Hello, this is GED Live at PALS with teacher Alex. Today's subject is GED Science and the topic is waves and energy transfer. Let's have a quick overview. We will talk about what a wave is. We will have a look at transverse and longitudinal waves, mechanical and electromagnetic waves, parts of a wave properties, specifically reflection, refraction and diffraction, and the electromagnetic spectrum. A wave can be described as a disturbance that travels through a medium or field from one location to another location, where particles oscillate or vibrate about a fixed position. Important to understand is that waves only transfer energy from one point to another, but not matter. Consider the example below: a duck sitting on the water without itself actively moving, and a wave passes through from left to right. How will the duck move? Will it move with the wave from left to right, or against the wave from right to left? Will it just move up and down and stay where it is? So the solution to the problem you will see here. While the wave is moving from left to right, the duck behaves like a particle in the wave, and it moves or oscillates around a fixed position. Water waves are a bit complicated, so we see a circular motion here. Why that is, we will see soon. Let's have a look at different types of waves. The direction of oscillation of the particles in waves relative to the direction of the wave or energy transfer can differ. In transverse waves, particles oscillate perpendicular at 90-degree angles to the direction of energy transfer. Examples include seismic secondary S waves of earthquakes and electromagnetic waves, for example. Longitudinal waves. In longitudinal waves, the particles oscillate parallel to the direction of energy transfer. Examples here are sound waves, ultrasound waves, and seismic P waves. Here we see an example of a transverse wave. The wave moves from left to right, and the particles in the wave move perpendicular to the wave direction at 90-degree angles, up and down. In a longitudinal wave, the particles move parallel to the wave direction. We can see that the wave moves from left to right, where the particles oscillate left to right about a fixed position. Now let's get back to the water waves. The water waves are a combination of both longitudinal and transverse wave, and that results in a circular motion of the particles in the water wave, where the circular motion is greatest at the surface and decreases with increasing depth. Another way we can distinguish between waves are mechanical and electromagnetic waves. Mechanical waves cause oscillations of particles in a solid, liquid, or gas. These mechanical waves travel through a medium by causing the molecules to bump into each other, like falling dominoes, transferring energy from one to the next. Sound waves cannot travel in the vacuum of space because there is no medium to transmit these mechanical waves. So mechanical waves always need matter, particles, as a medium to be transferred. Electromagnetic waves cause oscillations in electrical and magnetic fields. Electromagnetic waves differ from mechanical waves in that they do not require a medium to propagate. This means that electromagnetic waves can travel not only through air and solid materials, but also through the vacuum of space. Parts of a wave. Waves are described using the following terms. The rest position is the undisturbed position of particles or fields when they are not vibrating. Peak is the highest point above the rest position, as well called the crest sometimes. The trough is the lowest point below the rest position. The amplitude is the maximum displacement of a point of a wave from its rest position, so the distance between the rest position and the peak, or the rest position and the trough. The wavelength is the distance covered by a full cycle of the wave. Most easy way to measure it is from peak to peak or from trough to trough. A period is the time taken for a full cycle of the wave, usually measured from peak to peak or trough to trough as well. Frequency is the number of waves passing through a point each second. Frequency and period are related to each other, which we can see in the animation below here. Frequency is the number of cycles divided by time, whereas the period is the time it takes per cycle. So in this case, we can see one wave takes 4 seconds. That means our period t is 4 seconds. The frequency tells us how many waves we have in 1 second. And in this case, this will be 1 over 4 or 0.25 waves per second. The unit of frequency is hertz. The wave speed equation. The speed of a wave is related to its frequency and wavelength according to the following equation. Wave speed in meters per second equals frequency times wavelength. Since frequency is the number of waves per second, when we times frequency by wavelength, we get the unit meters per second, which is the unit of speed. Properties of a wave. Waves undergo reflection, refraction, and diffraction. Reflection involves a change in the direction of a wave when it bounces off a barrier. The law of reflection states that the angle of incidence equals the angle of reflection. Angle of incidence and reflection are measured using the normal line. The normal is constructed by using a 90-degree angle from the surface where the ray hits the barrier. Diffraction of waves involves a change in the direction of waves as they pass from one medium to another due to a change of the speed of a wave. When a wave passes from a medium where it travels faster into a medium where it travels slower, the wave will bend towards the normal, as we can see in the picture below. This is an example of light traveling in air and going into glass. Light travels faster in air than in glass, so the light bends towards the normal as it slows down. Diffraction involves a change in direction of waves as they pass through an opening or around a barrier in their path. Here we can see a wide gap relative to the wavelength. The lines represent wave fronts, so the distance between two lines is equal to one wavelength. We can see that the gap is a lot bigger than one wavelength. If we make the gap smaller, the amount of diffraction increases. We get the most intense patterns of diffraction usually when the gap is about the same size as the wavelength. Electromagnetic waves. Energy that is produced by the movement of electrically charged particles is called electromagnetic radiation. We can see the electromagnetic spectrum here, from low energy waves on the right, radio waves, to very high energy waves on the left, the gamma rays. The type of wave here are electromagnetic waves, and they're all the same. The only difference is their wavelength and their frequency, and hence their energy. Frequency is directly related to the energy of an electromagnet or of a wave in general. That means the higher the frequency, the higher the energy of a wave. All electromagnetic waves as well travel at the same speed in vacuum, the speed of light, c, with 3.0 times 10 to the power of 8 meters per second. Or more precise below, 299,792,458 meters per second. Uses and dangers of electromagnetic radiation can be seen on the right in the table. Each type has a unique set of uses based on their wavelength, frequency, and energy. Radio waves, for example, are used in radio station and wireless communication. Microwaves in microwave ovens to heat water, and weather radars, or for Wi-Fi. Infrared is used for remote controls and thermal imaging, and so on. Let's have a look at some questions. Using the dot as the starting point, place an X on the wave to indicate one wavelength. That would be in this position here. Visible light has an approximate frequency of 300,000 GHz or higher. Based on its frequency, the wave in the diagram represents which type of wave? You can pause the video if you want to think about the answer. The correct answer here is radio waves. It's the only wave that has a lower frequency than visible light with 3 GHz. Let's have a look at 4 more questions. What do waves transfer? You can think about the answer and pause the video. Answer for question 1 is coming now. Energy, but not matter. Question 2. How do oscillations move in a transverse wave? You can pause the video. The answer is coming now. At right angles to the direction of the wave. What is the name of the distance from peak to peak of a wave? The correct answer here is wavelength. What is the period of a 4 Hz wave? The correct answer here is B, 0.25 seconds. Since the period is the inverse value of the frequency, the inverse or the reciprocal value of 4 is 1 over 4, and 1 over 4 as a decimal is 0.25. If we have 4 waves per second, that means one wave will take 0.25 seconds. That was GED Live at PALS with teacher Alex. The subject was GED Science and the topic was waves.